So during this class we'll be discussing a lot about semiconductors and transistors, and I really want to stress the point that transistors are actually the engine of ICT. Let's say all the incredible, extraordinary development of information and communication technology has been possible because of the power and the performance provided by the semiconductor technology, which is quite recent. So I really want to highlight this point and to provide you with a context. Semiconductor technology is a relatively recent type of technology. There are a few important dates. The first one is the 1947, close to Christmas, end of the year, because that is the time the first transistor was invented. The first, let's say, three-terminal semiconductor device which could behave as an amplifier. Okay? Before this date, the only possible amplification of electric signal was with vacuum tubes. After 1947, also semiconductors could provide a way to amplify electric signals. And so this is an important date. The other important date is 1961, because this is the date of the first integrated circuit. So the possibility to fabricate on a single piece of silicon a complete electronic circuit with transistors, conductors, resistors, and so on. So a complete circuit fabricated on silicon. Why was that so important? Because then it provided a technology that could be scaled industrially from a relatively small number of transistors. Here, in the first integrated circuit had only 6 transistors. Okay, in a disk with a diameter of a little bit more than a couple of millimeters. Okay? But this technology had an incredible potential because you could increase the number of transistors and make transistors smaller and smaller. And this is why, in a few decades, it was possible to put more than 1 billion of transistors on a single piece of silicon. Okay? This was, and the date that made this possible was 2010. This is an i7 processor by Intel with a technology that is called 32 nanometers. We will see what this exactly means now. So this is the corresponding layout of the integrated circuit. You see there's a significant difference. Actually, this has a diameter of about a couple of millimeters. This is something like 1 centimeter by 1 centimeter, so it's a bit larger, but not that larger. The reason why you have 6 transistors here and 1 billion here is that, of course, transistors are much, much smaller. So, and the possibility to pack these transistors in higher and higher density and with smaller and smaller feature size was possible because the technology was intrinsically scalable. And of course, when you go from here to here, the capability of the electronics in terms of signal processing, in terms of computation in general, change a lot. Okay, so okay, why is that? So when we say that transistors are smaller and smaller, we really need to, let's say, have an idea of how smaller they are. They are smaller than a virus. Okay, the number that I mentioned before, 32 nanometers, in the past was a number that indicated the gate length. So this is the longitudinal cross-section of a transistor, a MOSFET. This is going to be the source. This is going to be the drain. This is the gate. This is a photograph at the scanning electron microscope. This is the gate, and the gate length used to be the number that defined the technology. Okay. For the 32 nanometer technology, that number is not exactly the gate length, because the number now indicates something more complex and less intuitive. But let's for the moment assume that still that is the gate length. So the main dimension, the most important dimension of the transistor. So in this particular case, this is not a very new transistor. It's designed from about 10 years ago. Already was basically smaller or more or less of the same size of an influenza virus, which is 100 nanometer in diameter. So they are really small objects that are present in huge numbers in a die. And this is something that really has a critical impact on how you design an integrated circuits with billions of transistors, and on the reliability that you need in production. Because typically, if one of those transistors does not work, the entire integrated circuit does not work. So you need a billion working transistors. In the case of memories, there are options to, let's say, have a working memory even if not all transistors are perfect. But in the case of logic, that is not the case. So in a processor, all transistors must work. So this is a very simple example. Why do we need all these transistors? How can we connect the number of transistors that we have with the capabilities of the technology? And just to have, let's say, an intuitive idea, I'm always doing this example. This was Atari Pong. It was a video game, one of the first video games by Atari. It went it was shipped to shops everywhere in 1976. I actually got it for Christmas in 78, something like that. Okay, in Italy things arrive a little bit late. But I was at the elementary school at that time. So, and of course you know what the game is. Basically it's a sort of ping pong. These are rackets. This means 0, 0. So you know the resolution of the graphics is incredible. I mean, it's something. I mean, it was let's say bleeding edge technology at the time. Of course, you had to connect it to a CV, and for this you need an integrated circuit with 2,000 transistors. So you still need 2,000 transistors for having this one. There was, let's say, the main microprocessor of the console had about 2,000 transistors. And if you go to, let's say, a modern video game, then you need something close to 1 billion transistors. And that is, let's say, of course, it's a very, very simple example, but this is the size and the change of the order of magnitude from 1K to 1 billion. So you need 1 million times the transistor you need to do that. With respect to those, you need to do this. Okay? And this is, of course, true for video games, but it's true for computation in general. It's true for control of, let's say, industrial systems and so on. Roughly, not exactly, but roughly in terms of order of magnitude, the computational capability of a microprocessor are proportional to the number of transistors you have. Okay? In practice, it's a little less than proportional, because when you have a lot of transistors, you start to use them not really in the best possible way. Let's say you don't use all the computational possibilities that you have. So it scales, let's say, less than linearly with the number of transistors. By the way, this was the main integrated circuit. This is the Atari. So I remember, I did not remember correctly the number of transistors. This was 300. This is 5 billion transistors with 8 Java cores for the PSP4. So again, the order of magnitude is correct. You need 1 million more transistors. So, okay, there is something that I would like to stress because it's also something that recurs again and again in the history of technology and in all the situations in which you have a change in the main technology that is used to accomplish some function that you need. So I was saying before that there was already an electronics industry before the invention of the transistor. Okay? It was already a very, let's say, vibrant electronics industry. And it was all based on tubes. Okay? Vacuum tubes, they are called in English. In Italian, sometimes they are called valvole, or tubi a vuoto. And it was a big industry in the sense that there were a lot of companies, and there were radios, there were TVs, there were also color TVs with vacuum tubes. Of course, there was already a telephone, or the telephone industry was already in place. And by the way, this invention of the transistor happened at Bell Labs, which were the laboratories, the research labs of Bell, which was the main telephone company in the US. Actually, it was the only one telephone company for all the US that basically had a monopolistic power, so really had huge amounts of money coming every year in, and so they really could afford to spend a lot of dollars every year in basic research. And these Bell Labs were really fantastic research labs working on basic science without any real application, and also on, let's say, advanced and very applied science. So the industry was already there and was also very sophisticated. Because if you want to make a color TV with vacuum tubes, you really need to be extremely sophisticated. Okay? And the point is that, at some point in 1947, December of 1947, it was really at the change of the year. So the patents were sent in December 1947, and the public release of the information was given in 1948. So this is why I have two different dates. So they announced the invention of the transistor. Okay. By the way, these three people here are the inventors. This is Shockley, this is Bardeen, and this is Brattain. Bardeen is this one. And they got, after 8 years, in 1956, the Nobel Prize in physics for the invention of the transistor. Okay, they proposed this device. They were able to show the possibility of amplifying signals with this device. But what happened is that actually there was already a technology for electronic circuit. And these semiconductor transistors were not that good. So basically, I mean, the only real advantage that they had is that, of course, they were smaller than the vacuum tubes, and that they had a smaller power consumption. But for example, from the point of view of performance and from the point of view of reliability, they were really terrible. So what happened is that basically not AT&T, Bell, the company, did not know what to do with the transistor. Okay, they really did not know what to do. They kept the invention for some time there, and then they started licensing the invention of the transistor for small applications to small companies. And the first applications were the ones that are shown here. So that basically exploit the only good thing that these transistors had, which was the fact that they had a smaller power consumption. So basically they could be used for portable things. Because of course, if you have a vacuum tube radio, you have to keep it in the dining room or in the office. You cannot move it because it's a heavy equipment. So the first application was this hearing aid. It's a very, very simple application. You have a microphone, and then an audio amplifier, and then a loudspeaker for people that have hearing problems. Basically, you're not exploiting high fidelity. You're not exploiting high performance. You're just using the fact that you can carry this piece of equipment with you. So this was the first application. And the second application is, let's say, a little bit more mass market, because it was a transistor radio. For AM radio, you can actually make a receiver with just one transistor, because you have to perform an amplitude demodulation that is relatively easy. Just one transistor is enough. So they made this one transistor radio. And of course, this is not the business of Bell. At the time, they were interested in, let's say, large businesses. This was just a gadget for them. So they basically licensed the technology to a small Japanese company that was called Sony. They just started doing these things. Okay? And of course, things improved for Sony and so on. So basically, the thing that I want to stress is the fact that sometimes when there is an established technology and a new one comes, the new technology is very bad at first. It has only small advantages in only a few different angles, and then only from them one can start to use the technology. But at some point, if it's good enough, then the technology improves and improves, and then eventually, let's say, take all the market. Because as you know, in these years, you never see a vacuum tube. Okay? Vacuum tubes are only used by, let's say, desperate fanatics of let's say, vintage audio equipment. Okay, but it's not really. I mean, it's a very small niche of the market. Nobody uses vacuum tubes anymore. Okay, so you never have to evaluate a technology that is starting with the eyes of what is the level of the technology now. You need to you think about how it can evolve, and because things can be very, very different. Okay, of course this was an interesting point, but then I was mentioning the fact that really changed everything was the invention of the integrated circuit. So the integrated circuit was actually invented in 1958, the patent. Then the first commercial integrated circuit was from 1961 by two different people, Kirby and Noyce, in two different companies. And as I mentioned, actually this very, very simple technology at the start actually enabled the possibility of increasing year by year the number of transistors that you can put on a single piece of silicon, and therefore the possibility to build more a more complex circuit. So I just want to connect the invention of the integrated circuit with something that you have heard many times in the news, the so-called Moore's law. I want to stress the connection of these two things because we are going to see why this is important from a quantitative point of view. But I now just want to stress the importance of the prediction. So the issue is the following. Basically, at a conference in 1965, the conference in the field of semiconductors, that in 1965 is becoming an important industrial field. Gordon Moore was the CEO and founder of a relatively small, medium company in the field of semiconductors, which was, at the time, Intel. And they were actually, at the time, mainly doing memories. Okay, basically static RAMs and static RAMs. That was it. And so at this conference, basically, he makes, let's say, some comments about what is the scalability of the technology. Okay. Based on some intrinsic limitations of the technology. And basically, he shows this plot, which is a very simple one. You have the year on the x-axis, and on the y-axis, you have the logarithm in base 2 of the number of components of transistors that you can put on a chip. Okay? And he basically says this thing. Okay, in 59, basically, we were just able to have one transistor on a piece of silicon. So 0 is 2 to the power of 0. Okay? Then in 62, we were able to put 8 transistors on a chip. 3. In 63, we were able to put 4 transistors on it, 2 to the 4, 16 transistors on a chip. In 64, we were able to put 2 to the 5, to the power of 5, so 32 transistors on a chip. In 65, 2 to the 6, so 64. So, and basically, he makes some consideration and says, okay, according to our predictions, there are no practical limitations, so we can continue to double the number of transistors per chip every year. And basically, he draws this line. Okay, so you need to consider this thing. He has 5 points and draws the line. And the reason why this is called Moore's law is that in practice, it almost worked. Okay, because if you, let me just, if you just look at the actual curve here, these are the points that I've just shown you. So this is the line. And these red and orange points are the actual products by Intel. The red squares are memory chips. And the orange ones are microprocessors. So basically, it's the same semi-log plot. You have the year on the x-axis and the logarithm of the number of transistors on the y-axis. So you see that basically the slope was actually a bit smaller at the beginning, and then it went up again, and now it's this stops at 2007, something like that. Now we are here, of course, but it's still with the same slope. It's continuing with the same slope. So basically, it was not a doubling every year. It was something more to a doubling every 18, 24 months, depending on the period. but still the slope is very solid, and for more than 50 years. From 65 to 2015, it's 50 years, so we already passed 50 years. So you can imagine if in the course of 60 years you're able to double the number of transistors every year or every 2 years, then you can go from 1 to 4 up to a few billions. Okay? And this is where we are now. We're now below 10 billion, but way above 1 billion. You probably, some of you have heard, have seen on the web the presentation of the iPhone XS. Okay, the iPhone XS has this new A12 microprocessor, and the A12 actually contains 2 integrated circuits, one for memory and one is the logic. And the logic chip has 6.9 billion transistors, and it's one of the. I mean, at that scale is one of the largest number that you can see. So the impressive thing is that actually this thing could work. Okay, just for curiosity, basically. Intel actually started with memories, then continued the line with memories. At some point, it stopped making memories, and it started with microprocessors. Actually, it started with microprocessors here in '71 with the 4004, which was actually the first commercial microprocessor. So now Intel is mainly known as the microprocessor company, but it was not the original product of the company. The original product was memories, and at some point they decided that they needed something. They needed to do something else. Just I want to show you something, but I have. So this is the 1404. It was the first microprocessor. It's an important product because it's the first time they put everything required for make simple computation. They wanted to make a calculator, a 4-operation calculator. Okay, very simple thing. But to put everything in one chip. And so Intel hired 3 guys, Hoff, Fagin, and Mazur. Fagin was the head of the team. It's this guy here. By the way, it is Italian, actually. It's from Padua. And he worked at Intel at the time. And so in three people started to design the microprocessor. They really wanted to make 4 operations. So, and they did it with a little bit more than 2,000 transistors with a 10 micron process. So a transistor at that time was 10 micron long. So compare 10 micron with 35 nanometers that I've shown you before, which means 300 times smaller. The clock frequency was 100 kilohertz, so quite easy, quite slow, but it was enough. And actually, it was. This is the layout of the chip. They could design everything by hand. Okay, at that time it was easy. I want to stress this point because this is a 2,000 transistor circuit. In 3 persons, they could work on it for a few months and design a complete calculator, 4-operation calculator on a chip. Of course, if you want to design a chip with 1 billion transistor, you need other tools. Okay, you need many more people. You need much more time, but you also need, let's say, very, very sophisticated tools to control the complexity of the chip that you have, because you cannot move inside the chip. Here, you really can just pinpoint the various transistors and say, okay, this is not working to me, you have to change this. But if you multiply the size by 1 billion times, 1 million times, you of course cannot do that. Okay? And by the way, Federico Faggin this evening is in Pisa. He's actually, there's a prize which is given to him by IEEE this evening in Pisa at Le Benedettine, just now. I cannot be there because I'm here, but it's I mean it's already the 4th time he's coming to Pisa to visit or to give seminars or talk to people. Now he's receiving a prize today. It's an incredible life. If you want to, let's say, have an idea about it, just check on Wikipedia. That's the whole story. It's discussed. He basically was a scientist that was an entrepreneur, then founded different companies. I mean, people my age, I'm 50. People my age know very well a microcomputer that was very common when I was, let's say, a teenager. There were 2 types of microcomputers when I was a teenager. One was the Commodore 64, and probably some of you have heard of it. You ask some of your parents in case, or they have to be my age because otherwise they don't know that much about it. And the other one was the Spectrum. They were similar, but the microprocessor on the Spectrum was called Z80 and was made by a company that was founded by Federico Faggin. He basically at some point broke up with Intel. They parted ways. He went on his own to found his own microprocessor company and made the Z80 for the Spectrum Sinclair, which was a huge hit at the time. And then that thing also finished, and he started a company which is called Synaptics, which made touch screens. And basically most of the touch screens around the world are made by Synaptics or on license by Synaptics. So, I mean, he made a lot of money in the process, of course. Yeah, by the way, just to put everything in the context, they wanted to make a calculator. So this thing went into this calculator, which was a very sophisticated electronic product for the time. It was, let's say, a sort of 4-operation calculator on paper, without screen. And at the time, those things required a few chips. This is the main board. I mean, this is a really vintage product. And of course, the challenge was to them the fact of, let's say, fabricating all the chips, basically. At first, they were asked to fabricate the memories, the RAM and the ROM for the chip. So all these other chips are RAM or ROM. And then at some point, they decided to also fabricate the microprocessor, which was the thing that had to, let's say, do the calculation with the ALU. And there was also a portable version. So I could find this way on www.vintagecalculators.com. So you find a lot of nice stuff. Okay. Okay, we will discuss from a quantitative point of view these issues in the next lectures. But now I want to give you the context. Now, of course, you're increasing the number of transistors per chip. This means that basically the size of each transistor must shrink. And is that good or is that bad? Apart from the fact that you can put more transistors in the same space. There are some advantages. There have been a lot of advantages. And because actually what happens is that as the transistors become smaller, they also become faster, and they consume less energy. So you can obtain an advantage in terms of higher speed in the computation and lower power consumption. Even if you have many more transistors, then you can perform many more operations at the same time. Okay? So, and these advantages are important and are really critical. So when you reduce the size of the transistors, you can have more transistors per chip, you can have faster transistors, and then each transistor can dissipate less energy. We will stress from a quantity point of view this point next time, not today, because when these things stop to be true, then it becomes much more difficult to continue the scaling down of the technology. And this is something that has happened in the last few years and is probably going to happen in the near future. So it is actually a critical issue. So this is, let's say, a complementary plot. Of course, here, instead of having the number of transistors per chip as a function of the year, you have the physical gate length, so the length of the gate, as a function of the year. And of course, as you expect, this is going to go down. So this is what happened. Actually, I graduated in 92, okay? And it was the newest technology, the technology to come. The actual technology was 1 micron, so 1 micron gate length. The new technology to come was 0.5 micron, okay? And then the nice thing is that at that time people said, okay, we know we can go down to 1/4 micron, but then probably we have to stop. And then 1/4 micron came at some point, and then people started to say, okay, we can go down to 0.1 micron, and then we have to stop. Nothing is possible. And then, of course, 90 nanometer came, and people started to say, okay, we can go down to 10 nanometer, and then we must stop. And then the thing is that it's continuing. I mentioned before the A12 chip. The A12 chip is made with a technology that is called 7 nanometer. Okay? It's not actually a 7 nanometer technology, but it's close to that. So actually, I mean, nothing is, things are not really stopping now. So one lesson for me was that you never have to believe the people that talk about the future, because nobody knows anything about the future. You never know. And actually, I'm making things a little bit too simple, but I want to stress this point. People were wrong at the time, because actually the various obstacles could be overcome, but in doing that, a lot of things had to change. It was not simply, up to a certain point, it was a simple scaling down of the technology, but after, let's say 12 years ago, it was really not possible to just reduce the size of all the features of the transistors. In order to reduce the transistors, you need to put a lot more innovation in terms of material and in geometry. For example, this is a transistor with, let's say, technology node that at the time was called 0.13 micron. and the actual channel length was 70 nanometers, 0.07 micrometers. You see, this is a longitudinal cross-section. This is the channel. This is, for example, the source, and this is the drain. This is the gate contact. Okay, so this is already, this is still a normal transistor. Okay, the larger ones were larger. This is more or less the same thing, but it's only smaller. So everything is scaled down, let's say, in an harmonious way. Things do not change dramatically. It's the same thing, but only smaller. Okay. Then, at some point, things had to change, and had to change a lot. And everything started in 2003, so more than 12 years ago. Now it's 14 years, 15 years ago almost. So what happened? Let me show you, because this is not always discussed, but it's really important. So in 2003, a technology node was introduced that it is called 90 nanometers. So at that time, still this number indicated the minimum feature size, the minimum dimension. Actually, in the process of fabrication, 90 nanometer was the defined length of the gate, but in practice, the gate became was a little bit smaller during fabrication. Things for some, let's say, issues with the fabrication, the actual gate length was a bit smaller. But at that time, what was necessary was that in order to keep the improvement that you need when you reduce the size of the transistor, the improvement in terms of speed, it was required to modify the material. And the way the solution actually was to provide strain to the material, which means really change the distance between the atoms of silicon in the crystal, because by doing that, you could change the property of silicon and improve the mobility of electrons and holes. Okay? And this was required in order to be able to reduce the transistor while improving performance. So this was a huge issue, because before finding that solution, people thought, okay, if we continue to reduce the transistor size, we do not have any improvement in terms of performance. So there's no need to reduce the transistor size. Okay. But still, actually, this solution was found to apply strain to the silicon. So the process was called strained silicon. And one possibility to put strain in silicon was to, let's say, inject germanium in the source and the drain regions with silicon, because germanium has a different characteristic length of the crystal, and so it tends to occupy a larger space and to compress the material in other parts. Okay, let's say this is a small detail that I don't want to stress to you too much. The important thing that I want to stress is the fact that already at that time, in order to improve the performance of transistors during scale down, one needed to introduce modifications in the material. Okay? You know that with the MOSFET you have silicon and silicon oxide and polysilicon, and that's it. Only silicon-based material. Already at this time, it was necessary to include germanium in order to change the properties of the material. In 2007, there was the same problem again, and what was done was to change the oxide of the transistor. You know, in the MOSFET, you have this silicon for the channel, silicon oxide for the gate oxide, and then the polysilicon gate. The silicon oxide had to be changed because the oxide was too thin and there was current through the oxide. So the oxide was leaky in the sense that current could go through the oxide, and you don't want that because it means a lot of power consumption. And then it was the thing that had to be done was to change the material of the oxide and to pass to a so-called high K material with a higher dielectric constant, much higher than silicon oxide. And in order to change the material for the dielectric, also the material for the gate had to change. Instead of polysilicon, it was introduced the metal gate. So a huge change in technology with many new materials introduced. This high K material, which is a very, let's say, very exotic material. It's called hafnium oxide. It's very different from silicon oxide, and also a metal gate in the place of polysilicon. So the important thing to remember is that from 2003, in order to continue the scaling down of the semiconductor technology, new materials had to be introduced. It was really it was a revolution in terms of material, because the only reason why silicon at first was used for transistors was that on silicon one could grow a very good insulator that was silicon oxide. If you put silicon to the air, it oxidizes and you have silicon oxide on top of silicon. Silicon oxide is a good insulator. Silicon is a good semiconductor. You have a perfect combination. And this is the main reason why silicon became dominant in electronics. Now, at some point in 2007, you say, okay, I have to eliminate silicon oxide to change completely. So you still continue to use silicon because already you have all the technology based on silicon. But really, it was the main reason you had silicon in the first place, the presence of silicon oxide. Okay. In 2011, another change occurred that we are living already now. That was a change in geometry. Transistors became vertical. You know the main type of transistors now, it's not the one that I've shown you before, but it's the so-called FinFET, which you basically have the channel that is vertical, like a fin, and then the gate is around 3 sides of the channel. So basically transport is in this direction. You have a source here, the drain here, and the gate that is around 3 sides of the channel. And this was a huge variation in terms of geometry, because everything had to be changed, and also the way in which you use the transistor and you design logic gates with the transistor had to change. Probably I have a slide here. This is related to the processes that I've shown you. Okay, this is good. Basically, just look at the picture now. This is the use of the high K metal gate process. The problem was that at some point, while you were reducing the size of the transistors, you started to have a very thin gate oxide. So you had silicon for the substrate and the channel. Then this was the oxide, and this was the polysilicon for the gate. So this has to be an insulator, but it was already 1 nanometer, 1.2 nanometer thick, which is a bit too little in the sense that you can have a lot of leakage current through this very thin silicon layer. And then, I mean, the change was to use a much higher layer of a dielectric with a higher dielectric constant, so that the capacitance per unit area is more or less the same, but you have a thicker oxide. In order to do that, you cannot have polysilicon on top because it does not grow nicely, you have to put a special sequence of metal layers on top, so that you have a metal gate, high K process. So the main point was here to have something thicker here, but still with a high capacitance per unit area. And the fin, okay, this is an illustration which is easier to understand than my mimic here. So you see the situation. This is the channel. This is a silicon fin. Here is the source, and this is the drain. And then you have the gate. The oxide, the dielectric is around 3 sides. And then you have the gate on top, which basically is on 3 different sides of the channel. So this is also called the Tri-Gate transistor. FinFET and Tri-Gate transistors are synonyms. Okay. And this is the main technology from 2011. 2011, we had the so-called 32 nanometer technology. It was introduced first by Intel at the time. Then there was the 22 nanometer technology by Intel, again with Tri-Gate transistors. After that, the so-called 14 nanometer technology by again Intel. But also other, let's say, semiconductor companies in these years have a Tri-Gate or a FinFET technology. And yeah, that's it. So in the last few years, huge innovations have been necessary, both in terms of materials and in terms of geometry. This is a cross-section. You see, they seem teeth instead of transistors. This is a cross-section, just cutting the channel into half. This is the channel. So in practice, it's not rectangular, the cross-section, but it's more triangular. And then this is the gate oxide, and this is the gate which goes on 3 sides. This is the 22 nanometer process, and this is the 14 nanometer process, which is, let's say, still smaller. Same size, smaller. Now Intel is introducing the 10 nanometer process, and then all these numbers do not mean that much now. They are just commercial numbers. Let's say, more or less they are commercial numbers, in the sense that you cannot really compare, let's say, the 10 nanometer technology by Intel with the 7 nanometer technology by another company, because these numbers, let's say, don't have a precise meaning anymore. Everything has become really more complicated, and it's difficult to compare 2 technologies by only looking at 1 transistor. One really has to consider a complete circuit and to look at the whole area occupied by the circuit. Okay, one thing with which I want to conclude this part is this point. The fabrication of integrated circuits, especially for microprocessors, for these very high densities, has become extremely expensive. Because all the equipment is so expensive that you really need a very large number of, you need to fabricate a very large number of integrated circuits in order to have, let's say, reasonable numbers. Okay, consider that one fab has a cost of order $10 billion now. So very few companies have the volume to be able volume production to be able to, let's say, afford the construction of a complete fab. And so what happened, basically, especially in the last few years, is that very few companies have remained in the business of fabricating high-performance integrated circuits. So if you look at, let's say, high-performance microprocessors, basically you only have six companies, and that's it. Okay? And some of those companies only fabricate integrated circuits for themselves. Actually, one of them only for itself. That is Intel. So Intel has its own fabs in order to fabricate its own microprocessors and to sell them. And this is it. In addition to Intel, there is Samsung. Samsung fabricates integrated circuits for Samsung products, but also for other companies. Okay? And then all the other four that are called TSMC, UMC, SMIC, and GF, which stands for Global Foundries, basically fabricate integrated circuits for third parties. They are just fabs. Basically, if you are, just to make the example that I made before, if you are Apple, Apple needs to fabricate a chip. They do not have their own semiconductor fab. They go to TSMC. And TSMC basically fabricates integrated circuits for third companies. They are called, in the jargon, foundries. Foundries like fonderie in Italian. Okay. A foundry is a company which fabricates integrated circuits for other companies. So, for example, Apple's only designs the integrated circuits and then asks TSMC to fabricate them for it. And that's it. So also SMIC, UMC, and GF are foundries. So the only companies that are in the game now of high-performance chips are these ones. All the other ones stopped already at some, let's say, older technology node. So they're able to fabricate something, but not the high-performance chips. For example, you cannot see ST Microelectronics here, because ST Microelectronics, for example, stopped at 28 nanometers. So they can fabricate a microprocessor for a car, for simple things, but not the high-performance microprocessors. Okay. Up to last year, Apple used to have their own chips fabricated by Samsung and by TSMC. So can you believe that Apple had its main microprocessor fabricated by Samsung, which is also the main rival. Now only the display is by Samsung. They use the fabs from TSMC. And this table illustrates the plans for the next few years in terms of technology nodes. So Intel is going now with 14. 10 nanometers should go out soon. This was delayed. It was expected to be out this year. It was delayed, then they're planning to go down to 7 nanometers. TSMC is already out with the 7 nanometers, which is, okay, Intel says our 14 nanometers is faster than 7 nanometers, but of course, you really never know. And Global Foundries has decided 2 weeks ago to stop. They're not going down. They're stopping here because they do not have enough volume to go into full production with 7 nanometers. So it's really a game which is becoming a few players game. Oh, this is South Korea. This is US. SMIC is China. This is Taiwan. These two ones are Taiwan. And the biggest one is TSMC, actually, in terms of fabricated chips. So it is a game for Asia, and that's it. It's really something that one needs to consider. Fabrication of high-performance chips for high-volume products is basically a business for Taiwan, South Korea, a little bit of China, and some base in the US because Intel is there. That's it. Okay, you can stop here, and then we make a small break, and then we start again.